Alright everyone, in this video we're going to take a quick look at the C++ standard template library, and I'll hopefully give you a pretty good idea of what the library is, why it's there for us, and why it's useful, and also most importantly kind of the basics of how we're going to go about using it. So first things first, the C++ standard template library is basically a collection of predefined classes and functions and types that are going to be available to us on any system we're developing on, right? There's no need to install anything because this library is basically part of the C++ standard. It's defined in the specifications to be there, and its behavior is defined for us. And the great thing about this library is it provides a lot of different classes and a lot of different data structures that are going to be really useful across many different applications, and they're going to already be defined for us, right? So in many cases, when you're working on a development task, you may know you need a queue, or you may know you need a stack or a list or something of that nature, but you maybe don't have the time, you don't have the money, etc., to fully implement these data structures, and beyond just implementing them, testing them to make sure they behave correctly, that you have no other errors that could cause you issues down the line, etc. So instead, when you're doing serious development and you're kind of short on time, you can just go ahead and use the classes that have already been defined for you. And using them is going to be as simple as importing a header into your program and creating an instance of the class, just like we've been doing all semester so far. And what you're going to note is, as we kind of talk about a couple of these, some of the behind the scenes plumbing of how they work are things we've already talked about, right? So by looking at these classes, you should have more than just an idea of saying like, okay, the queue works in a first in, first out manner. If you look at the functions that are available to this queue, you should also be able to kind of deduce what the implementation looks like, because it's probably going to be very similar to the implementation we already did, right? But the benefits here is they've been predefined for us. The code has been reviewed many different times, and it's probably going to be much more efficient than any of the code we're going to write straight out of the box, right? So basically, when you're doing real development work, you definitely want to make use of these sorts of classes. And what makes these classes so useful is the whole idea of them being a standard template, right? So when we declare an array, or we declare a list, or we declare a map or a queue or something like that, we're not hard coding in the data into these structures the way that we have been, right? So in previous examples and previous assignments, when we've made our trees or we've made our lists, etc., we've created the struct, and that struct had both the data and it also had pointers to the other structures as well, right? So the class we defined was kind of also dependent and kind of hard-coded in the type of data we were storing. If we wanted to store a string, we had to put a string member inside of the struct that made up the backbone of our data structure. If we were storing ints, then we would have to create members for those in the structure, etc. The beautiful thing about the standard template library is all of these classes are basically data agnostic. We can store anything we want right away without having to rebuild or modify any of the implementations of it, right? The array class here does not care about what you're storing in the array. It just needs to know how big the piece of data is that you're trying to store, and then you can shove an int in there, you can shove a string in there, you can shove a whole nother struct in there if you want to. And this holds true for just about any of these structures, right? And I'll kind of show you how that all works in just a moment here, right? But it's just important to know that these are container structures for the most part, which you can see they kind of define here a little bit. And that basically just means these are containers around any data that we've already defined, which make them super useful, right? Because you can quickly create a queue of anything you want. You can quickly create a stack of anything you want. It doesn't really matter, right? Because all of the heavy lifting's been done for us already, right? So one of the best places to look for information on the standard template library, if you're interested in learning more about this, is basically at cplus.com/references/stl. This is going to be the best place to go to learn about the classes that are available and also learn about the functions that are available to perform on those classes, right? So for instance, let's just take a look at the vector class. All right, so we can click on this vector link here, and this is going to take us to another page, and this page basically has all of the documentation for the vector that we could possibly want. This documentation is basically going to include the types it can accept, which it's a template class, so it can accept any type, some behavioral notes, and also kind of tell us what some of the properties are of the container that we've selected. Now, if you don't know what a vector is a extremely useful container type. Basically, you can think of a vector as a dynamic array, and you can use it more or less as both how you would use a normal array, but you can use special functions on this array, on this vector, to add new elements to the back of it, just like you would a linked list, but then you can still go ahead and index into them just like you would an array, which is super useful and very, very helpful. Right, so we have our container properties. We know that it's being stored in a sequence as they're added. This is a dynamic array, and it's allocator aware. That just basically means it knows how to clean up after itself when it's destroyed. And then at the bottom here, we have basically members of the class. So these are, pieces of information you can get back out of the class. And then you will also have functions you can use on the class as well, right? It lists out its constructors, its destructors, its operators, as well as various properties and iterators you can call on the class, right? So we can get the size of the vector, right? Get a list of how many elements are in it. We can get the current maximum size, so this is how many elements we can add to the vector before it's resized. We can tell it to resize itself. We can tell it to shrink, etc., etc., and then we can also call different functions to access elements in different manners as well, right? So this operator square brace basically means we can index into it just like we would an array. We can get the front of the vector, the back of it, we can get access to a specific element with this function, etc. And then there's also various other functions like push back, pop back. These are just like we would do basically with a stack or a queue to remove elements or add elements. We can insert elements at specific indexes, erase, swap, clear, in place, etc., etc. Basically, any useful operation you could want to do on a vector is basically listed here. Right, so this is going to be the number one place to go to get information about a class that you might be interested in. And the next best thing about this website is if you're interested in a specific function, you can click on that specific function and it's going to give you a very nice example of how to use it, right? This is what makes this website so wonderful. It gives you very good information about the data structure, and it also gives you very nice, concise examples about how to use the data structure and the specific function you're interested in, right? So it gives you a great amount of detail to make your life much easier in figuring out these data structures. Now, one thing to note when you're going through the library, and if you're looking to use a specific function, make note of basically this itty bitty little gray box down here. And if you look very closely, you'll see that this gray box basically says C++11. So what this means is that this specific function that we're looking at is only available if you are compiling against C++11. Now, just like any other program out there or operating system, etc., languages have different versions. And as a language grows and gets older, new features are added, some features are removed, etc. as new versions of it are released. With C++, there's currently probably 5 or 6 different versions out there, with the de facto one that most compilers compile against by standard being C++ 2003, and C compilers being C98, potentially. I'm not sure about the C side, but typically we need to compile, or we by default compile against C++ 2003 just for compatibility reasons. If you want to use any of these functions, then you need to compile against C++ 11 or newer, which is done by specifying a flag to the compiler as you try to build your program. That's really all there is, but you can take a look at them, and we'll see what that looks like here in a second. If you want to read more about C++ and its different versions, you can take a look at the wiki page for it. It's pretty interesting, and there's actually some kind of cool stuff in here, as well as it also lists the different current standards of C++. All right, we have C++ 98, 03, 11, 14, 17, and apparently 20 will be coming out as well. The one interesting thing to note is there was a huge change between C++ 03 and C++ 11. In 11, there was a whole slew of new features added to kind of improve C++ and kind of make it more memory safe and a bit easier to use. Right? One of the design goals was also to attempt to try to make it easier to teach. Whether those goals were really met, I'm kind of on the fence about, but hey, other people might have different views, just because it does bring some of those features into the language that we had in Python and Java, etc. I guess it depends on what kind of enthusiast for the language you really are. Right, so this is the standard template library, and there is lots of good stuff in here. This is by far not going to be a comprehensive video. It's just going to be enough to get you going with it and kind of show you what you can do with the library. So one of the best things to do is to kind of just show you a quick and easy example of what using this library actually looks like and some of the things you can do with it. Right, so for instance, I'm going to show you basically the vector, just because this is one of the structure, or one of the data structures I find most useful and actually find myself using quite a bit. So if we want to use the vector, the first thing we need to note is kind of what do we need to include in order to make use of it, right? Because if we just start trying to use the vector here, then I can go ahead and type vector or something, but the compiler isn't going to know what it is. So to use the vector and its associated functions, what we can do is pound include, and we can type vector. Right? The nice thing about the STL library is if you want to use that specific data structure, they also name the header to include the same name, right? So if we want to use a vector, we include vector. If we want to use a queue, we pound include queue. Want to use the array, we pound include array, etc., etc. Pretty straightforward, right? Now, what we would initially think is to create a vector, we would just say vector myvec, right? Because that's how we declare it. We have declared everything else so far. But what we're going to find is if I do g++ strcpp, we get this error, and it basically says unknown type name vector. Did you mean hecto? Blah blah blah. Whatever hecto is, I don't even know what that is, right? But what we need to remember is we are dealing with template libraries, right? So that means these are, when we first say vector, we are basically saying we're talking about this wrapper class, right? That's going to wrap around some piece of data. But what we need to do to make the compiler happy is basically tell it what sort of data we want to store. All right, so if we go back into our code, what we need to do to make the compiler happy is we type vector, but then we also put angle brace int myvec, right? And what goes inside of the angle brace here is basically the type of data we want to store. So what this line is saying is create a vector of integers that I can store data in. All right, so we save it, we compile it, and now we compile fine, and everything is happy. Right, so okay, great, we have a vector. Now how do we put data in it? How do we use it, etc.? So with the vector, if we go back to the page, we can look at the functionality that's available to us. And what we want to look at is the modifiers, and we can see what functions are actually available to us. And you can see we have a function called pushback, which all it does is add an element to the end of the vector. So to use it, it's going to be just like we've used any other class so far. We would do myVec dot pushback. I think it was an underscore, right? Yep. Pushback, and we want pushback 5. And after that, we can do cout myVec, and we can do element 0, right? Because if you remember, right, a vector is a dynamic array. So we type that, we save it, we compile it, we run it, and you can see we print out 5. Now, if we wanted to add more numbers to the list, it is basically as simple as going int I for I is equal to 0, I is less than 10, excuse me, I plus plus. And then we can go ahead and do myVec dot pushback, and we're going to do I. Right, and then after that, we can do, we can do the same thing again, and we'll go ahead and print these all out. There we go. Compile it. Oops. I have a stray. I knew I was supposed to delete that. Compile it again. And there you go. 0 through 9 is printed out. So that's basically how we put data into the vector and how we push data back out. So now, great, that's how we put an element into the vector without, knowing anything special about where it should go, right? We don't know how big the vector is at that point. We just call pushback, and our data gets put into it. And then we can go ahead and print it out by accessing vector 0 or index 0. But now let's say we had more elements we were putting into the vector. Right? So if we had int I for I is equal to 0, I is less than 10, I plus plus. Right, we can go like that, and then we're just going to stick I into this vector. And then we can go ahead and start printing elements out. Now, the one question that there's going to be is, okay, if we put some arbitrary number of elements into the vector, how do we iterate over all of those without accidentally going out of bounds and causing a seg fault and having all sorts of issues, right? Luckily, because this is a class, right, and the class has metadata associated with it, we can take advantage of the functionality that's available to us to write a loop which will iterate over all of the elements and print them all out for us. All right, so again, we have for I is equal to 0. And now we can do while I is less than myVec dot size I plus plus, we can go ahead and print out the contents of the array or of the vector, right? And we'll take that to I, and there we go. Right, so size, or the size function, basically returns how many elements have been inserted into the vector thus far. Right, you can call size, and it will print out how many things we've added. Right, so this lets us write a little routine, which will go ahead and run it and print out all of the numbers that we have in the array without us ever hard coding how many elements are there or what indices to use. Right, so this works, this works really well for things like arrays, right, where we can index directly into them. But what happens if we start using some of the other more advanced data structures that are available to us? Right, over here, that's not the one we're... Over here in the containers, you can see we have quite a few different types. We have basically queues, we have sets, which is basically just like the mathematical set, an unordered group of items. We have forward lists, which are basically singly linked lists. We have the list, which is a doubly linked list. The map, which is basically like a dictionary from Python or Java, etc. Right? So how do we create some standard way to iterate over all of these elements without getting stuck in the weeds about, okay, are we traversing linked lists, or are we indexing directly into arrays, or how is this all happening for us? And luckily, C++ and the C standard library basically has a way to do this, or help us with iterating over all of the elements in any of the collections that are available to us. Right? And believe it or not, the thing we would use is actually something called an iterator. Right? An iterator is yet another templated class that we can use in conjunction with any of the other containers that we might want to iterate over. Right, so for instance, let's say we did not have any clue about the size of this array or of this vector, and we didn't want to have to call myvec.size every single time we ran through the loop, right? Or we just didn't want to index into this for some reason. There could be other reasons why we'd want to use iterators, but this is just a good way to show you how they basically work. So to create, the first thing you need to do is basically create an iterator. And so to create an iterator, what we do is we use the same basic prototype we use to first create the structure that we're iterating over, right? So we have a vector of ints, and then we're basically going to use the namespace resolution operator that we've talked about so far, and then we're going to say iterator, and we're going to call it, right? So this basically says create an iterator which will be able to iterate over a vector of integers. Right? So once we have this iterator, then what we can do is we can still use a for loop, and in the for loop we're going to say for it equals myvec.begin, and while iterator does not equal myvec.end, right, then we're going to do ++ it. All right, so this basically says create a loop. The .begin function returns an iterator to the beginning of the container, which is it, and then while it does not equal the end, or the iterator that is at the end of the structure, go ahead and increment the iterator. And when we see this ++ it here, this is not the simple I++ or ++I that we see here, where we are just, adding 1 to something. This is an overloaded operator with a lot of stuff going on behind the scenes, right? So with this ++ it, or it++, whatever, basically what's doing is it's doing a whole bunch of math and a whole bunch of work behind the scenes that says, okay, we know we have this specific structure. We know each element of the structure is this size, so go ahead and move us to the next element. And that could be by doing simple math and using array indexing like we normally would, or that could be traversing linked lists behind the scenes. The important thing is that we've abstracted that all away, so all we really know or really care about is just the fact we're moving to the next element in the collection. That's the only thing that really matters. Right? Once we have that iterator, then what we can do is we need some way to get the data that's pointed at by that iterator. And to do that, we just basically do a simple dereference like you would normally do if you were passing pointers around, right? So we could do cout dereference it, and we're going to print off a new line there, right? So this dereference basically says go get the data that is being pointed at by the iterator, right? Again, if we were creating collections or containers of more complex data, then we would need to cast this basically into a structure that we could access the individual pieces of. But because we are just getting or dealing with integers right now, this should work fine. All right, so we're going to go ahead and save it, compile it, and run it. And you can see here this first 0 through 9 was our normal for loop, and this second 0 through 9 was basically the iterator for loop. And the great thing is, like I mentioned before, ooh, what new feature of Z Shell did I create? No. I don't know what I just fell into here. Okay, there we go. Anyways, as I was mentioning before, the great thing about iterators is we can basically change to a completely different structure, and the iterator is basically going to stay the same, right? That's the great part about it, right? So let's say, for instance, now we no longer want to use a vector. Instead, we want to go ahead and switch it up, and we want to go to a list, or in this case, a linked list, right? And the behind the scenes structure here is basically we're dealing with a doubly linked list, just like we've seen before, just implemented for us. All right, so we pound include list, and now we say we want to create a list of integers. I guess we'll call this list for ease and less confusion. Right, so we go ahead, we create the list, and then the function to actually insert data into the list is basically still available to us is pushback, because this is a doubly linked list. Right, so we can go to list, we can click on the class, and then we can take a look at the functions that are available to us, and in the modifier section we have push front, pop front, in place back, push back, yada yada yada. Right, so really nothing much is going to change here other than the name of the thing we're using, my list. And then to iterate over the list, right, we're going to go here, my list, and actually create an iterator for that list. And now when we compile this and run this, you're going to notice we're going to get the exact same behavior, right, as we would expect to. All we're doing is inserting a bunch of numbers into a structure and getting those numbers back out. But the important and really cool thing is we just completely changed the backing data structure, and all we had to do to implement that and completely change the structure we're using is include one different header, create, I guess, one main type and one iterator, and that's all we had to do. If we wanted to change the names, we would have had even less code to change, right? So we just completely changed the structure of the way we're storing our data with practically no effort, and that's really awesome. Or at least I think it's really awesome. All right, so we'll go ahead and compile it and run it, and there you go. We get the exact same data again with minimal changes, even though instead of us storing it in an array where everything is contiguous in this one giant block of memory, we're now storing everything in a linked list where things are scattered all over the place. But we don't know it, and that's really the fundamental thing about using classes and using interfaces, etc. This stuff is all completely transparent to the end user, even though things are completely different behind the scenes. Okay, so hopefully that's given you a little bit of insight into what the standard template library is and basically how to use it. If you have questions about, please go ahead and ask me. I'll answer them the best I can, as well as, hit up the C++ website. That's arguably the #1 resource to go look at when you want to use some of these C++ standard template structures. And one other thing before I close the video is just if you want to use any of these functions that are only marked as being in C++11, to use that you would just implement them like you would in your code, but then when you go to compile it, the extra flag you're going to tack on there is standard equals C++11, hit enter, and you'll compile against the newer standard of the language. If you were looking at using something in 14, just change it to 14. If you want to use 17, you change it to that, even though my compiler doesn't recognize 17 right now. I have a slightly outdated one, but it still works. But, alright, that's all I have for now. Again, if you have questions, don't hesitate to ask me, and we'll see you in the next video.